All right, so this is the start of the lecture number 2 on physics, where we're going to deal with our system of units. So, our unit system in physics, which is going to be the MKS system of units. And another name for this is called the SI system, which stands for Système Internationale. It's French or Italian, I think, for the international system. Basically, it's a flavor of the metric system. So I'll write that down here at the bottom. This is basically a certain flavor of the metric system. Oh gosh, lordy. What's the deal with the MKS system? Well, it's based on M's and K's and S's, and the M's stand for meters. Actually, that should be a lowercase m, and meters are a unit of length. Now, how long is a meter? How big is a meter? Well, a meter is about the same as a yard. A yard in the imperial system runs 36 inches. A meter winds up being 39.3, I think, inches long. So it's just a little bit longer. If I held up a meter stick and a yardstick and I didn't put them right next to each other, you would not probably be able to tell the difference. However, when you start getting a lot of meters, like a football field is 100 yards long, but if you made a 100-meter long football field, you would notice it. It would be a few extra feet long. In fact, we might have fun calculating how much longer it is. I first noticed this when I was golfing in Scotland, and I came up to this par 3 hole and it said 160, but they measured it in meters. I thought it was yards, so I pulled out like a 6 iron or whatever I hit, and then it was woefully short of the green because that turned out to be 185 yards. The K does not stand for kilometers, it stands for kilograms. And this is what makes it a flavor of the metric system is we're going to use kilograms as our base unit instead of just plain old grams. And that's a unit of mass or heft. How much heft is it? What kinds of things are a kilogram? Well, a kilogram is about 2 pounds. If you buy yourself kind of a standard package of hamburger, particularly the one that's in the tube shape, usually it's 2 pounds of hamburger, and that's a kilogram of hamburger. You would not want to make a kilo burger because putting 2 pounds of hamburger into a single patty is going to create a structural nightmare and or a cooking nightmare. How do you get the heat to penetrate to the center without the outside getting charred beyond belief? People who work out are familiar with this because the big heavy plates, the big plate is 20 kilograms, which is 45 pounds. So the last one is S, which is seconds. And seconds are, of course, a unit of time. And a second is about one human heartbeat. About. Everybody's got a different resting pulse rate, but the standard resting pulse rate is 60 beats per minute or 1 per second. Fit people may be down around, I don't know, 40, 45, and people who are not fit and drink tremendous amounts of caffeine can have resting pulse rates closer to 80 or 100. You do need one more unit. I mean, you can put these units together to make other units, like you can put meters squared to make a unit of area, meters cubed makes a unit of volume, meters per second makes a unit of speed. But you need one more unit to really finish it out and make all the other scientific units. And normally people say that that unit is the degree Celsius. And that, of course, is a unit of temperature. A degree Celsius is about 2 degrees Fahrenheit, but they do have a different starting point. But it only takes 100 Celsius degrees. What did I write? Celsian? Wow. Celsius. It does take 100 degrees Celsius to cover freezing to boiling of water, whereas it takes about 180 Fahrenheit degrees. That makes Fahrenheit degrees a little smaller, maybe a little finer. I don't know. Um, So that brings us to one more thing about this. Why did we do this? Why didn't we just use the standard metric units? Why did we throw in kilograms here? The answer is that all of these units are of a human scale. A yard is about a human wingspan, from the center of your body to the tips of your fingers if you're a 6 foot person. 2 pounds. Well, 2 pounds isn't a human. I guess our internal organs might go 2 pounds, but you only need about 70 of these kilograms to talk about a regular human. This, of course, is based on a human heartbeat, which was the first timekeeping device before people figured out pendulums and watches and whatnot. So these are all human scale units. Even though the science of physics studies the super, super small or the super, super large, we use human size units. And that's where the metric system comes in, because if you need to be studying something that's very small, you're not really going to be measuring it in meters, or at least not full meters. They'd be fractions of a meter. So this is where the benefit of the metric system comes in, because the metric system has a system of prefixes. And these metric prefixes allow you to create units that are of the scale you need for the job at hand. And that's a letter that goes in front of the unit and modifies the unit. So let's talk about this. Let's make a little cloud right here. And this is going to be our base unit, whatever it is, meters or seconds, or even things like bytes for computer memory. If you put a small c in front of it, you're going to say centi, and that's going to be a hundredth of the unit, or times 10 to the minus 2 of the unit. So that would look like centimeters if you wanted to make a smaller size thing than a meter. And in fact, a centimeter is a hundredth of a meter. It's about the width of your pinky finger or a marble or something like that. Then if you put a small m in front of it, you say milli, and that's a thousandth. And that's times 10 to the minus 3. I know these two are close to each other. They won't all be that close. So a millisecond would be a thousandth of a second. A millisecond is faster than you can press a button 2 times in a row. I know because I tried it. Actually, it's very few milliseconds is the time it takes a signal from your big toe to reach your brain. So a nerve impulse from your big toe doesn't get to your brain for a couple of milliseconds. That means that human beings think of everything that happens within about 2 or 3 milliseconds as being happening at the same time, because your body collects all the signals. That also means that if you drop a hammer on your toe, you won't know about it for a couple of milliseconds. The next one is micro, and that's a funny Greek symbol called a mu. It's a long stem on the front, like the stem you might put on a lowercase p, but instead of putting a loop on the end, you go ahead and put a lowercase u on the end, and we say micro, and that's a millionth, or times 10 to the minus 6. A micrometer is a very small size. In fact, you'll hear sometimes people abbreviate micrometer as micron, and a micron is pretty small. I've seen filters on things, HEPA filters, and they say it's a 3 micron filter, which means it's really going to filter out all the dust particles and things that are in the air, even ones that are almost too small to see. But a 3 micron filter will not stop something like a virus, which is much smaller. So the N95 masks that medical professionals are wearing when they're in contact with people that have viruses, they have a much smaller pore size, a much smaller hole size, big enough to let air molecules like oxygen and nitrogen through, but not big enough to let the virus through, or at least very readily. Then the last one in the small side is a lowercase n, and we say nano. And a nano would then be a billionth, or times 10 to the minus 9. Really, honestly, you can replace, so a nanosecond is a very short period of time. One of the problems with making an atomic bomb is, at least when I say the atomic bomb, I mean the uranium bomb, was you had to compress the uranium into a small size and you needed to set off explosive charges all around the outside to squeeze the core of the bomb and make it go off. But they all had to go off within a nanosecond of each other, and the electronics and the switching and the timing of doing that was really well beyond a lot of people. So when the Americans made the atomic bomb, it was very difficult for anyone but the Russians really to copy us. So basically, you take this nano, this n, and you replace it with times 10 to the minus 9. So 1 nanosecond is actually equal to 1 times 10 to the minus 9 seconds. And if you want to see that written out, go ahead and put that in your calculator in scientific notation. Use the exponent key, so the times 10 to the, this would be the exponent key or the EE key on some Texas Instruments calculators, and put 1 EE minus 9, and you'll get a decimal point, and you'll get a whole bunch of zeros, and then you'll get a 1. Now, things that make it bigger, make the unit bigger. And if you're studying things that are bigger than humans, you might want to use units that are bigger than humans. So first thing you can do is put a K in front of it, which we've already seen with kilogram. We say kilo, or killa, sometimes people say, and that is 1,000 of things, or times 10 to the 3. So we've seen our kilogram, and we're familiar with kilometers or kilometers. Above that is capital M, to differentiate it from the lowercase m, and that is mega. And mega is a million of something. Oops, there we go, fixing it up. Or 10 to the 6 of something. So I've seen megabytes before, megabits per second, this kind of stuff. Megabits per second is probably something you've seen in terms of a data rate or something like that. And then above that is the letter G, and we say giga, not giga, as Doc Brown did in Back to the Future, but giga, which is a billion. And that is times 10 to the 9. So we've seen gigabytes. I've heard of gigawatts of electricity, which is what a very large power plant would be putting out. We know that there's a letter above this. There are all kinds of letters. There's even letters in between, but these are the ones I need you to memorize, not only for this class, but for your life. If you're going to use the metric system, there's going to be prefixed things. But there's a letter T for tera that would then be times 10 to the 12, because they follow this nice, even sequence, with the exception of centi. Centi, thank you, Romans. The Romans were fascinated with breaking things into hundreds. A centurion was one of 100 soldiers in a unit. And that goes to this day, almost every currency. The coin is 1/100th of the regular unit of the currency. So we have this one that breaks the mold here, but other than that, it's every 3. Just like when we're writing big numbers, we put a comma every 3 letter or sets of 0 or what have you. That's a very common thing to do. So this is kind of the secret right here, is that the letter is just that power of 10. That makes it easy to convert. Okay, I'm going to stop here. This is a very short lecture today, and I'm going to put it up,